All right, this video is 12.4 independent events. So we have talked slightly about independent events, but we're going to go into it more deeply. What does it mean for two events to be independent? So let's start by looking at some definitions. So an independent event is when the occurrence of one event has no effect on the occurrence of the other event. So we're talking not statistically, probability wise here. So we're saying, does the probability of the first event occurring affect the probability of the second event occurring? So mathematically, we can check independence by using this formula. If the probability of A intersect B is equal to the probability of A times the probability of B, if those two things are equal, then that means that the events are independent. Okay. If we get that the probability of A intersect B does not equal the probability of A times the probability of B, then we will know that the events are dependent. Okay. So we don't always have to check mathematically in order to tell if they're independent or dependent, but it's always a good idea, right? So the first one says draw a card from a deck of cards and get an ace. So the probability of drawing from a deck of cards and getting an ace would be, whoops, sorry, let's try that again, would be 4 out of 52 because there's 4 aces in a deck of 52 cards. So put the card aside, so that means we don't put it back in the deck, and now we're going to choose from the deck again, and we're going to see if we get a king. Now, so the probability of getting an ace is 4 out of 52. On the second draw, the probability of getting a king is going to be 4 out of 51. Now, if I were just to draw one king out of a deck of cards, normally the probability would be 4 out of 52, right? So because this probability of getting a king has changed slightly, because now we only have 51 cards in our deck instead of 52, these are going to be dependent events because the probability of the first event occurring affected the probability of the second event occurring. Now, if we would have, instead of taking the ace and setting it aside, if we would have taken the ace and shuffled it back into the deck, then these events would be independent because getting a king would still be 4 out of 52 if I were to have replaced that ace back into the deck. So these are dependent. So these events are dependent. Okay, so let's go ahead and look at the second one. Draw a card and get an ace. Replace the card in the deck and draw a king. So now this time, because we're replacing that card, that first ace, back into the deck and then shuffling it again and then drawing again, now our probability for drawing a king has not changed. It would still be 4 out of 52. So in the second one here, these events are independent. Okay, on the third one, drawing out a blue marble from a bag of 6 red, 2 green, and 3 blue. Throw the marble back in and grab a second marble that's green. So because we threw the marble back into the bag, these events are going to be independent. So we call this with replacement or without replacement. So if I'm just looking at some events and I know that whatever was taken was replaced, then I know that the events are going to be independent. If they are without replacement, that means the second probability is now going to be affected because if the first event occurred, I'm not putting that marble or that card back. These events would be then dependent upon one another because I am not replacing it. I'm not giving that back so that the bottom number here on the second one would change, and sometimes the top one, depending on what the probability is. Okay, so some of these questions are just asking you to think about it. Are these dependent or are they independent? Okay, show mathematically whether the events are independent. This is using a two-way table. So on this one, because it asks us to show mathematically, we really need to use our formula. That is the probability of A times the probability of B. Does it equal the probability of A intersect B? Now, if this is true, then they are independent, okay? So if they are equal, then they're independent. If they are not equal, then they are dependent. So we need to check this. So the first one is asking us, is the event that a flight is on time, this is going to be event A, that the flight is on time, and then the event B is going to be that the flight is domestic. Okay, so let's look at what is the probability that the flight is on time. So it looks like there are 162 out of 180 that are on time. So we're going to take the probability of that event A happening, we're going to multiply it by the probability of event B, which is that a flight is domestic. So if I look up here, there are 120 out of 180 that are domestic. Now I need to check, does this equal the probability of A intersect B? So remember, the probability of A intersect B would be the intersection of on-time flights with domestic flights. So domestic and on-time, there would be 108 out of 180. So grab your calculator, multiply these out. Remember that when you're multiplying two fractions together, you actually need to multiply the top times the top. So 162 times 120 is equal to 19,440. And then I also need to multiply the bottom times the bottom. So 180 times 180 equals 32,400, which comes out to, let me hurry and check, 19,440, oops, divided by 32,4, that is equal to 0.6. So now we need to check, does 0.6 equal 108 divided by 180? And that's equal also to 0.6. I just checked it. So they are equal. And so these are independent events. Okay, so the question was, is the flight being on time independent of the domestic flight? So the answer would be yes, they are independent. Okay, so let's check the second thing here. Is the event that a flight is international, so now international flight is going to be event A, independent of the event that a flight arrives late. So arriving late is going to be event B. So what's the probability that the flight is international? Well, there are 60 out of 180 international flights. What's the probability that the flight arrives late? There's 18 late flights out of 180. And I need to check, does this equal the intersection of those two things? So the intersection of international and late. So late and international would be 6 out of 180. Okay, and I'm just gonna go ahead and put those in my calculator. If you do that, you're gonna get 0.033 repeating for both. So yes, these are independent. All right, let's go ahead and try another example here. The two-way frequency table shows data for 60 randomly selected children at an elementary school. Determine whether a child who knows how to ride a bike and a child who knows how to swim are independent events and prove it mathematically. So the child who knows how to ride a bike, knows how to ride a bike would be 45 out of 60. So we're gonna call knows how to ride a bike event A, and a child who knows how to swim is event B. Okay, so remember, we're just checking, is the probability that event A occurs times the probability that event B occurs, is that equal to the probability of A intersect B? If they are equal, they are independent. If they are not equal, they are dependent. So probability that a child knows how to ride a bike would be 45 out of 60 times the probability that they know how to swim is 40 out of 60. Does that equal the probability of the intersection of knows how to ride a bike and knows how to swim? So that would be 30 out of 60. So this side would be 50% or 0.5. And I'll check the other side quickly. And that does also come out to 0.5. So remember, multiply the top times the top divided by the bottom times the bottom. So 0.5 equals 0.5. They are equal, so yes, these are independent. All right, guys, good luck on the assignment today. If it asks you to show mathematically, then you need to do this formula. Otherwise, you can just think about it sort of and reason through it like we did on the first few examples. If you have any questions, email me, and have a great day.